Hello and welcome back to the combo classroom this time. I'm Domotro, and for those who haven't seen the last few streams, yes, I did amalgamate and quantify the percent of you that wanted me to shave my hair versus not, and shaved off that percent of the hair, which was about 40 to 50%, and it is temporary. The stream gang is going to get a slight sneak preview of a few things that the others may not get to see. And the others will get to see all of this once I drop a cool finale episode that's looking like it's going to be in somewhat late of March, about a week from now, which will be a whole wrap up of what I call grade -1 out here. As I've hinted, we are moving toward grade -2. Many have wondered why we are going deeper, but really we are increasing the absolute value of the grade number still. And I think it makes sense, instead of trying to head toward 0 and then toward the grades that people already did in school, to head the other way, further from 0 toward that realm. And for those who have wondered about if there will be imaginary grades someday, there certainly could be something along the lines of a grade I for some side project, but it probably will not be in the main chronological grade order of combo class. That will probably be descending toward the negatives. Thank you to everyone who's joining me so far, and to anyone who happens to be watching this out of my newer subscribers, welcome. We've been flying up in subscribers really fast here because YouTube decided that some of the shorts that I put out a while ago, they still like a lot. It's very funny that it really can be hit or miss on those things, where a decent short on here, I might get 10,000 views that are mostly people who are already subscribed. But this one short where I divide by 0 that I made a while ago, that short is still getting more views than any of the newer ones. So they decided they love this one where I divide by 0. Kind of trips me out because one of the most important projects of my life are some books I'm writing, and one of the important fiction books that I was writing before I ever dropped any combo class, before I filmed that, begins with a divide by 0 error. Divide by 0 errors were very important in this piece of fiction I made that relates to iterations of myself seeing things mirrored in their reality. And so I'm not the type to overanalyze coincidences as far as dedicating my life to them, but it was certainly a coincidence that tripped me out a little bit when the divide by 0 error was by far the biggest on not only here, but also on TikTok and etc. It's the most viewed combo class video twice. So on 2 different apps, have more views than any other of the videos. Weird. In any case, I will be dropping some more bonus videos on this channel for those who want a full in-depth math thing in the meantime, because the finale that I'm dropping will be a little more toward the end of nature and philosophy. I'll also be putting out the answers, or my set of solutions, to the test that I put out, the optional final exam of grade -2. Of grade -1, before we shift to grade -2, which I put out in a video on the combo class channel. In the next day or two, I will be putting out the answers to that on this channel, so people can look out for that tomorrow or the next day. And it's also just going to be either a fun thing to watch, whether you've seen the exam or not, if you want to see me problem solve through some problems on there. And it can be something that you can choose to skip if you're still working on the exam, or you might try it in the future. We will also be talking about a little bit of math today, as well as some brief clues about the state of transition that we are in here in the combo classroom, and why there's far more room here than typical. We have an amount of space that I was able to put up a tent in some of my previous streams. And here we don't have the tent going anymore because it rained last night, so I had to remove the tent after getting in a good campfire and such. But And the tent will be included in the finale episode with some more details about where that fit into my month. But in this stream, apart from analyzing some clues about what's to come and what's currently going on in the extra space here, we will also be looking at Mod 3, which is the sort of third, usually the second step considered in tiers or lands of what's called modular arithmetic, because usually similar to with what I call a basic base, a integer base, sort of like base 10 or 6 or 12 or 2, that plays by the same rules as each other, can't really include base 1. You have to redefine how you're using digits if you want to call tally marks base 1 in the same way binary's base 2. For one reason, because binary uses 0 and the number 1 below the base number. And so for base 1 to play the same rules, it would only use zeros. So a lot of times you start the bases at 2. You also often start modular arithmetic at 2. As we saw in our first episode, when we're looking at usual modular arithmetic, this cool thing that you can do to whole numbers, we're not really going to be using mod 1 much. We're typically going to start on mod 2. And it has a lot of similarities to the last digit a number would have in base 2. It also is secretly the patterns of evens and odds. And although we went into that briefly last week and stuff, I will do a brief refresher, which is if I say a mod number, 2 analogies you can think in your head for what's going on is that if that clock had a 0 instead of the 12, a 12-hour clock that ranged from 0 to 11 as its hours would have its hours going in mod 12. Clocks basically do, but they turn the 0 into a 12, which confuses things. But from 0 to 1 less than the mod or base number, you get a lot of cool rules, a cool set of things to work with. And clocks work like modular arithmetic as a good analogy because we know that 13 hours on a clock gets you to the 1 again. And it's true that in mod 12, 13 is called congruent to, which is written like an equal sign with 3 things in it, like a triple bar equal sign, and basically means like equals does in this modular arithmetic realm, although the difference is that 13 isn't the only thing congruent to 1, 25 is congruent to 1. 25 is also congruent to 13, although typically you'd simplify it to the easiest possible one, the lowest. And if you tell a computer, run the modulo operation, it's going to interpret it to put it as the lowest positive integer in that range. But we can also say there's these whole congruence classes, like the whole family of numbers that land on 1 on the clock. 1, 13, 25, negative 11, tons, an infinite amount of numbers are in the congruence class that we can say that number is equal to, in modular terms, is congruent to 1. And so clocks are a good reminder, but we can also think of it as just remainders to a degree. Remainders undersells its abilities. But remainders are a good way to grasp onto the first things we'll use in the modular tables, which is if we say a number is congruent to something in a given mod, it is, if we say it's congruent to A mod B, then it's A more than a multiple of B. So thank you all for the loving comments. I will check the comments relatively frequently in this stream because it's I'm gonna have them open here as long as I just have the camera on me. I don't know if I'm gonna be pulling my computer screen up, so feel free to leave any questions and stuff. And in the meantime, I will be continuing my modular rants throughout today's stream. Don't worry to those who can't catch all of the editions of all the episodes of the ones I'm going to call something like Modular Mondays. A lot of these thoughts will be condensed into either episodes on the main Combo Class channel or into things like the book about Threeven numbers that I am working on writing. But to those who have the time to stick around here, you will learn extra. You will not only be ahead of some of the others in some of the knowledge, but you will also just get more details, more interpretations, and more examples. And so, as we're going from, and some people request that I, on my main channel, make the things less cut down and just more include all my thoughts. And some people request on this channel that I edit it more so it's more like quick and digestible. But that's kind of why I have two channels. If you ever want something really quick and digestible, you might want to go through either the shorts on this channel or the episodes on the Combo Class channel. And then when you have time to want to hear the uncut version, that's more like the videos and streams on this channel. Someone requested the Collatz conjecture, and I will be talking about that at some point. Ironically, we will be bringing up Mod 2 when we bring it up. It has relation, there's an interpretation of it that binary is interesting to analyze it. So, for those who want Collatz conjecture stuff, that will be coming, but it's one of many topics that I almost mentioned in a live stream or made a short or bonus video here about. But when I really looked at my notes, I was like, I should wait until I'm ready to make a main episode about this, because the scope of the notes that I had was a little bigger than I wanted to just put on a random thing here. So there's a really cool connection between the Collatz conjecture and binary. It's not gonna be something that when I tell you this, you can crack the Collatz conjecture. A lot of people are interested in it because they think they'll get some clue to crack it. Well, if that's your goal, you better dedicate, 10 hours a day for many years to it, because there have been many, many hard minds at work for a long time on it. And I find it actually interesting to read people's supposed proofs of it, because you'll come across proofs of it that use relatively elementary concepts and are short. And if you're well enough versed in math or how history works or things, you know that it's very, very unlikely that somebody using basic elementary arithmetic and just a cool idea is going to be able to, within a page, prove this thing that so many minds have dedicated their lifetimes to. And so don't get your hopes up for being the one to solve it. It's going to probably require, if it's solved, one of those, things along the line of what it took to crack Fermat's last theorem, hundreds of pages of information from many fields that wasn't possible until many, many different fields culminated to stacks of knowledge that you had to pull from and combine. And I will talk about the Collatz conjecture, but I will also I'll also, as a disclaimer, note that I don't think it's the most interesting problem in number theory. I think it would say a lot about the capability of what humans can or can't prove. So the techniques it would take to prove it could be incredibly powerful techniques we would have to develop. However, the result we would get of whether we prove it true or false is somewhat close to meaningless. It's very coincidental random. We're going to go 3x plus 1. We're going to go over 2. There are many similar functions that are also unsolved. There are many, many similar problems you could come up with that are equally hard to crack. And it's a good example of that type of problem because it has evaded being solved. And so it represents a particular category of problem that if we crack it, we will have very powerful techniques that will be super useful. However, whether or not everything falls into the 4-2-1 loop or not is somewhat irrelevant to what we know about numbers. So, and of course we would know more about numbers, always good to know more, but I would not hold the Collatz conjecture, despite its mass talked aboutness, to the level I would hold something like the Riemann hypothesis or even the twin prime conjecture. Or many others like Goldbach's conjecture, the ABC conjecture, and there's a lot of other big scale ones in number theory that I haven't talked about all of them yet. So somebody is saying it's 3 a.m. yet they're still watching. That's cool, although sleep is good. I'm not great at getting my sleep these days, so, well, I need to work on my sleep schedule too. But Someone asked what got me into math. Um, I can't give too long of a detail to all these because I do want to go back to the mod stuff. I always get distracted fleshing out things with extra details, and as usual, I got distracted explaining mod 2 enough that we didn't even get to mod 3 yet. But what got me into math isn't probably a singular thing because I was always interested in patterns, and numbers have very cool patterns, and I liked playing around with numbers because they gave a cool grasp on patterns. And I remember that although I've done a lot of my current math studying, starting 3 or 4 years ago, I got super deep into math and started reading an insane amount of math books and stuff, which I've done at times in my life in the past. But the most dedicated I got to like reading math books as one of the main hobbies of my life started maybe 3, 4 years ago. But throughout my life, I've had many times where, looking back on it, I had some sort of deep interest in experimenting with numbers or playing with them or learning about them. And a few little ones that stand out are in middle school, me and my friends would play a lot of games when we first found out about types of numbers. So, like, I remember there was this one called the 4 4s challenge, trying to build numbers with fours. That was also when I first found out about factorials. And I remember that was a fun game. And then we found out about pi and the fact that it was irrational. And so we would try and memorize a ton of digits of pi. Me and my friends went for who could memorize 100 digits first. And it's still imprinted in my brain forever. The beginning, 3.141592653. And so some of it's just stuck in there. And we got really into Rubik's Cubes. And another thing that I really got into at the time was logic puzzles. I read some books by the author Raymond Smullyan, who wrote a lot of fun recreational math and logic books. And they had a lot of puzzles where certain inhabitants on an island always tell the truth, certain inhabitants always lie, and sometimes other rules about the island. And you had to listen to some dialogues and figure out certain details. Those were really fun for me to hear and to invent. And I got really into the golden ratio when I somewhat stumbled across it myself in a story I'll explain more about someday. And by stumbled across it myself, obviously I don't mean I was the first to discover it, but I mean that I did stumble into it before I read about it, because you can stumble into it by wondering things like, which number's square is one more than that number? And so there was a lot of things like that that got me into math, and I will give more examples in the future. And I kind of explained the half beard at the beginning of this. For a more detailed explanation, you're going to have to wait for the finale episode. I will say it's temporary, but it's going to last another week or so. So then after that, the rest is going to look more like this for a little bit. And then I probably won't cut my hair again for a little while. So probably by mid-grade -2, we might be back to this. All right. And let's see. Thank you all for the comments. Getting back to mod 2 and mod 3. So our mods can be seen as remainders, as clocks, as last digits and bases, and they actually can also be seen even deeper when we get to group theory, because these mod tables can show up within groups, and those things can describe so many things. So that is a large topic we will get to at some point in grade -2 or 3. So remember that these mod tables will continue to show up in more contexts. But the main context so far that we want to keep in mind are the clocks, the remainders, the last digits of bases, which are all happening at the same time. And by remainders, I actually find it easier not think about I divide by the number, what's the remainder, but how much more than the latest multiple of that is it? Like if I say it has a remainder of 2 after being divided by 7, a little easier to think about as it's 2 more than the latest multiple of 7. So the other thing we're going to think about it as is for mod 2 and 3, we got great nicknames for those. Mod 2s are evens and odds. Mod 3 is our threvens and our 2 types of throds. Of course, I'm still working on my game plan of my series of events that will get threven in the dictionary over the course of this year or next year. But So Threeven's not in any official dictionaries. Absolutely scandalous. But you should see the list of words they're adding to Merriam-Webster's and Oxford before Threeven. Absolutely ridiculous. So we are going to try and make sure that if there's any journalists watching this or any writers or people who run any sort of media of any sort, drop the word Threeven here or there. It'll really help when I try and make a Wikipedia page, and don't try and help me out on this. It will actually undercut the goals if people try and do these things first and then I do it. But when I make a Wikipedia page that is genuinely super full of dense of knowledge about multiples of 3, also known as Threevens, there's a chance they'll take it down without the right citations. More likely, they may remove the bit that says also known as Threeven. So it will really help if we have some sort of article that was written in a newspaper or something where I can cite that under also known as Threeven. Now, how does Mod 3 explain the Threevens? Well, where's a pen? I cleaned up my classroom, and we're at the state where, thinking about it now, my whiteboards are more accessible than ever, and I have no idea where I put my clean pen, my good pens. So, these, yep, we got a red color today. All right. So, we are going to get this whiteboard, the big old grade negative whiteboard, back in focus. Now, this grade negative 1 whiteboard has done so much teaching. There have been times where sometimes I go back to littler whiteboards, but I am going to need to re-get some mini whiteboards. All the mini whiteboards were not waterproof. Those are dead. The rain destroyed all the mini whiteboards. They are now in the trash. But there was a funny scene of getting rid of them in the finale. And the big whiteboard, though, despite a little bit of paint that got on the bottom during my episode about Threevens, funny enough, we got a good whiteboard set up here. This thing has helped me get so much teaching done. In fact, if you look at the first episode on the main combo class channel, you can see me unwrapping this for the first time. Now, you should at some point in the next week watch on the combo class channel the short intro episode that happened like almost a year ago. Well, it actually took place slightly more than a year ago, but it came out slightly under a year ago. Because some of the themes in that will be called back to in the finale. Now, also, my chair is sinking. Do you see how I'm just like going sideways? I don't know if you can fully see this, but when it's muddy enough here, the chair just sinks. I'm not doing that intentionally. It just goes. So, yeah, to add to the surrealness of the landscape, whenever a guest comes over, if they sit in one of these pointy chairs, it just sinks down half a foot. Okay, I should have used a less pointy chair, but we'll roll with it. Now, let's make some Threeven charts. What types of numbers are there? In Mod 3, you got numbers that are congruent to 0, 1, or 2. 2 could also be known as -1 at times when convenient, because in this mod, 2 is -1. Now, a more common default would be, unless there's a reason to go 0, 1, 2, 0, 1, 2, but there will be times where it'll be useful to write this as 0, 1, -1, 0, 1, -1. In fact, the nicknames that I give them do reflect that fact. These are Threeven, which is an obvious nickname that many people from history have probably thought, why isn't that in the dictionary? And these are ones that I thought needed a more specific name than the obvious Throd. And so these ones I titled Post-Threeven Throds. Now, we could, just call it Post-Threeven if we want, and that implies Throd. We could also just call it a throd if we're just saying it's either a 1 or a 2. And then the 2s I didn't call like double post 2 after, I called them pre-3even throds. So the nicknames actually are more reflective of this having a -1 status in the mod throd. Now, if the -1 being 2 feels weird, just imagine you got a clock that goes 0, 1, 2, 0, 1, 2. Well, if you go back an hour from the top, you're on 2. Now, let's see. I'm going to have to, I do want to respond to the comment about correlations, but I'm going to have to do that after a little more of this. So I will get to the correlation comment in a minute. Here we have some types of threeven and throd, and two really helpful tables to make here are what happens with addition and what happens with multiplication. Now, if I made a big times table, or let's do addition first. If I made a big like addition table of what happens when I add any number with another. And let me see if I can get a darker pen. This one's not being ideal. Nope. Okay, we're gonna use red for now. Worst case scenario, I have markers indoors that work. So here, if I have a table and I'm wondering what happens when I add numbers with each other, I would make sort of like the addition version of what you might call a times table, but you might call this like a plus table or something. Now, let's just start with 0 and 1, because we can note that in addition, normally this table would go 0 plus 0 is 0, 0 plus 1, or 1 plus 0 is 1, and 1 plus 1 is 2. However, if I was in mod 2, we get a shift there. We get that normal table, or in a mod higher than 2, these go to 2 for addition. But if I was in mod 2, they go to a 0. What does this tell me? This tells me odd plus odd is even. Now, we get a shift there for mod 2 on addition already, where mod 2 changes something about the normal routine this corner of an addition table would have. But what about multiplication? Well, if I turn this to multiplication, these ones become zeros, because 0 sort of wipes out all those. And 1 times 1 is 1. Now, if I analyze this corner of the times table, or I analyze the realm of mod 2, it's the same. But that's actually sort of weird, because usually mods are different. They have some sort of looping around that occurs. Mod 2 is sort of too small under multiplication to have any looping around. We don't ever pass 1 to get to the reset to the next 0 or the next 1 or etc. And so under multiplication, we actually don't learn that much by talking about I'm in mod 2 as opposed to talking about I'm in the corner. It really helps if you want to know about your evens or your odds or last digits in binary. But just analyzing the traits of multiplication here, I'm getting the same corner of the table as I would get otherwise. However, in mod 3, kind of like how in addition, mod 2 was enough to glitch it, mod 3 is the first one that glitches something under multiplication. By glitch, I mean that it's different than what this corner of a normal times table would be. We still get 0 times anything's 0, 1 times anything's that thing itself, but in this case, we get something different. 2 times 2 is no longer 4. 4 here has gotten to another 1. 4 is post-3ven. So we get a 1 there. Now, this is actually sort of neat because it means that under addition, this mod 2 table told us interesting stuff. But under multiplication, it's sort of like mod 3 is the first to introduce this shift. Now, I need to plug this in. Luckily, I don't think I need to move it too far because I have an extension cord that's longer now. One sec. Okay, stream will be saved. Cool. So, here in our mod 3 land, we have enough room for cool patterns to emerge. If you're just looking at the mod 2 zone, for example, the mod 2 zone's still living here in the mod 3 zone, sort of. It's telling us different things now, because 1 does not mean odd in this realm. 1 means post-3ven Throd, but we still see a similar look of those zeros in the 1, similar here, except for a little glitch. This can tell us actually many notable things, like, for example, that I've mentioned how the diagonal of mod tables tells us all the spots where a number hits itself in multiplication, so it tells us all of the possible squares in that mod, because any square number is gonna be 3ven times 3ven, post-3ven times post-3ven, or pre-3ven times pre-3ven. It's gonna be one of these diagonal spots. And so, if we look here, we can note what's on the diagonal. Oop, this one doesn't work. What's on the diagonal? 0, 1, 1. And there's no 2's on the diagonal, and as I've phrased that fact, this means square numbers cannot be n squared is not congruent to 2 in mod 3. And that's sort of interesting. It means no square numbers are 1 under a multiple of 3, which sounds kind of random. You're like, there's so many square numbers. Is that really true? But it is true because they follow this pattern. 0 squared is 3ven. 1 squared is post-3ven. 2 squared, post-3ven. 3 squared, 3ven. 4 squared, 5 squared. 6 squared, 7 squared. 8 squared, 9 squared. 10 squared, 11 squared. So you could make like a cool pattern out of that where you... Sorry, I'm just seeing if I have markers that might actually work. What about this fella? Nope. Okay, we're using the light red one for today. But it tells us that square numbers land in a certain spot in mod 3, which wasn't true in mod 2 when we had that little corner and it meant evens and odds. We had 0s or 1s. Square numbers can be even or odd, and they fall in a very predictable order. It's like an even number squared's even, an odd number squared's odd, so the square numbers are going to go back and forth. Even odd, even odd, even odd. But here we get a more interesting pattern that people don't point out. 3ven, post, post, 3ven, post, post, 3ven, post, post. And so the diagonals of these are super notable. That's just the beginning of what they're useful for, and they're called the quadratic residues of a given mod. So the quadratic residues mod 3 are 0 and 1, and the sometimes on the list you might see them just list the non-zero ones, because that will always be there. 1 will also always be on these typical mod charts. There may be sometimes you see them list other ones mostly, but technically these are quadratic residues, and 2 is a non-residue. So there's also cubic residues and onward, and cool rules about what makes which residues have what rule. It's one called quadratic reciprocity. We'll get into stuff like that later, but the main thing we need to note here is that certain types of numbers, if I run them through mod 3, some types of numbers on mod 2 as well, if I run certain types of numbers through, I'll hit a recurring pattern of what all the things in there are. In fact, if I run the Fibonacci sequence through this mod, I will get a recurring pattern. The Fibonacci sequence will have more of a repeating cycle than it looks like, but a different cycle in different mods. And that is going to be a whole episode someday. There's also other types of numbers we could analyze, such as numbers that are composed of 2 neighboring numbers multiplied together are known as pronic numbers or oblong numbers, because sort of like a square number could look like a square. They could look like an almost square, n by n plus 1. And, or equivalently, we could call that one n, and that one n minus 1. And so those would be 0 times 1, nothing. 2 times 0, nothing. Or 1 times 2, 2. So those pronic numbers can be congruent to 0 or 2 in the mod, but not 1. So a pronic number in mod 3 can only be threeven or pre-threeven, whereas a square can only be threeven or post-threeven. We can even look at what happens with triangular numbers. However, looking at the modular patterns of triangular numbers is sort of just a tease for a really cool pattern, because I'm not sure how many of you know of Pascal's triangle, because I've sort of purposefully been holding off on mentioning it because there's so many episodes hinged around it, and I want to make sure people see not just the typically known things about it, but some of the crazy cool things about it when I start dropping it in our episodes. And it will be coming pretty soon in grade -2, because it has relationships to these things called figurate numbers. And those are the numbers like square numbers, oblong numbers, also known as pronic numbers, triangular numbers, things that you could make a geometric arrangement of dots or cells or something that represents an amount of things so that it can be turned into an integer in an integer sequence, essentially, like the triangular numbers or the square numbers. And so when you look at Pascal's triangle, which is this really cool triangle of numbers, the reason I haven't gone into it yet is because there's many ways that we could define it. We could define it as you make each cell by adding the 2 above it, and you have a layer of 1s on the outside. We could define it as these things called binomial coefficients make up the rows to the sideways, if I'm looking at it sideways. So going down, it's like following these addition rules. Going sideways, we could define it by binomial coefficients. And what if I look like diagonal? Well, it turns out that these are all 1s, natural numbers, triangular numbers, tetrahedral numbers, which are basically 3D triangular numbers, or sums of triangular numbers, and 4D triangular numbers, 5D triangular numbers, and etc. So Pascal's triangle is all about triangles, not just because it's triangle shaped, but because it's like the triangular numbers meta family lives in there. And that's something I don't know why it's not mentioned as much. I mean, it's a true mathematical fact that a lot of people know, but people always act like the only triangle thing going here is the shape. But people always forget to mention that no, this triangle is the, what I call, hyper-triangular numbers. So when we go into that, it'll be hand in hand with going into different types of figurate numbers. And the cool thing about this is if I color the mods or if I color all the numbers in Pascal's triangle different mods, I get cool fractal patterns. So fractal in the sense that as you zoom out, they continue to have different scales of detail, and they are similar to the smaller scales in this case. And there's going to be a whole beautiful episode that we'll have to make someday about the patterns when you put this whole thing into mods. And because of that, if we look at triangular numbers in a given mod, that's looking at this little slice of the cool pattern. So it's kind of like an unfair tease to try and show you anything about this slice until I just show you the whole thing here, which won't be in too long because I've already been training y'all to understand mods, and so it's going to be a pretty quick connection once we introduce Pascal's triangle in early grade -2 to throw somewhere in an episode some of those fractal patterns. So Mod 3 is in some ways the first mod with enough room for certain patterns to expand or become interesting. Sort of how reminiscent to me of other ways 3 can be the first to grow under strange things, like 2 to any amount of hyper operation, which are the ones beyond exponentiation like tetration, to another 2 is still equal to 4. Because 2, let's say it was 2 with 3 of them, that means 2 pentated 2 means a tetration stack too tall of 2's. So that's like that, if you write tetration that way. And that means an exponentiation stack too tall. Oh, no. Yeah, that means an exponentiation stack too tall made of 2's. Okay? And that means a multiplication thing made of 2 2's. Okay? So they all break down to 4 because you include the base in the amount of them. And so under certain rules you can come up with, 2 doesn't grow even when you give it a bunch of stuff, but 3 would. If you replace either of these 2's with a 3, this is unspeakably large. And so, like, literally on this one where I have the 5 arrows between it, if I replace either of these 2's with a 3, I don't think it's the type of number that any computer can store. And so 3 can be the first to grow sometimes, and there's some of that existent in the mod tables, where there wasn't enough room in mod 2 to give much details about squares. They include all of the options are quadratic residues. There are no quadratic non-residues. But in mod 3, we get different categories for square numbers, for pronic numbers, and other stuff. Now, mod 2 does have room. It's still super useful and cool, but part of this mod 3 having enough room to grow is what got me started on investigating 3-even numbers so much, and is why I am trying to write a whole book about 3-evens and odds. And as I've hinted, due to the fact that evens and odds also get a lot of credit in the book, the true hero is mod 6. The mod where 3-evens and evens have a 6 cycle of combinations. So mod 6 is really the true hero because it gives us the details about 3-evens, evens, and pretty much nothing more. Also, base 6 is the best, just by the way, for humans. So those are some things about mod 3. Let me get back to the comments, and then maybe we will do some more mod 3. And maybe I will also talk more about the mod 3 and mud 2, the muddy sequel to the last time it rained back here. So, somebody's saying that when root 2 is geometrically finite, why do we have infinite decimal representation of it? Many numbers are like that. In fact, if you were able to somehow have a way of picking a random number on the number line, it's almost guaranteed it would have that property. And the reason is because to have an infinite decimal representation does not mean that you are infinite in size. It means it takes infinite fractions to describe you in a way. Because if I try and make a number like 2/3, I know that that is not only finite, but it's, well, no, actually, I'm thinking of an infinite non-repeating one. You didn't even mention it having to be non-repeating. So a lot of a lot of numbers have an infinite decimal. Arguably, everyone does. You can argue that if I write 2.5, there's infinite not needed to write zeros after there. So that is technically true in many ways, and we don't need to write the zeros or discuss them when we're saying what digits are in it. Like, I wouldn't say there is a 0 digit in this because it doesn't make sense to say everything has a 0, but technically there's an infinite amount of zeros after there. There's also technically an infinite amount of zeros before there. So every number arguably has that. Not even to get into the thing that these numbers have 2 representations. This is also 2.4 with infinite 9s. That's a debate for another day, but it's true. And to have infinite just means, if you're not counting this, if you're like, okay, well, don't count the ones that have infinite zeros. To have infinite just means that it didn't fit into a fraction involving tenths neatly. Because if I have something like 0.125, that's 1/8. And it ends up being able to stop there, meaning there's just the unwritten zeros after. And so it stops there eventually because 1/8 is just made of 2's in the denominator. And we're in base 10, which is made of 2's and 5's. But if I try and write the number 1/3, it's infinite 3's. And that's because base 10 sucks at handling thirds, as well as handling threvens. And here, speaking of which, if we look at a family of number, as for what traits they have here, none of the numbers with illion in the name are threven. All the numbers with illion in the name are post-threven. Like million, billion, trillion. That's a problem with our base. Too many fevens, divisible by 5, not enough threvens. But here, going backwards, a divide by 3, very threven-esque, but not a threven number, we have an infinite amount just because our base didn't have a spot where it rounded off correctly, because our base is only made of 2's and 5's. But what's happening in the infinity there is 3/10 plus 3/100 plus 3/1000 plus 3/10,000, etc. And that's a geometric series that adds up and does not ever pass the number this. It doesn't pass 0.4, for example. And you could try it if you add up 3/10 plus 3/100 and etc. You will never find a point where you get to 0.34 or even 0.3334. You'll never get anything bigger than this, but you will get closer and closer to this because you'll keep adding 3's. Similarly, you could look at the infinite 9's as one argument, or look at the video I made on this channel that's on this channel, but is a full video, like on the videos tab, about the harmonic series, because that explains how some infinite series can add to a finite thing, while others could diverge to infinity. And this is I didn't mention how it's also in decimals in that episode. It was already pretty long, that video. I mean, not technically like a combo class episode that's on my main channel, but I made a video to clear up some similar misconceptions about infinite series, which are secretly going on here. So most numbers are going to not be expressible in base 10 without needing an infinite amount of stuff. Even, fractions like 1/3, let alone an irrational number like square root of 2, that would not only have an infinite amount of decimals, but it would be not repeating. In whatever base you wrote it in, it wouldn't have a repeating period going on forever at some point. It would always be doing different stuff with at least some digits in any base you wrote it in, of the typical, basic bases as I call them. And so square root of 2, for, a number of reasons, will require an infinite amount of info to try and write it in base 10. But that infinite amount of info is describing smaller and smaller fractions added up. And if I'm going smaller and smaller at a rate, it might not pass a certain thing. And we're already kind of told that with the number. If you look at an approximation of what's the square root of 2, it's about 1.4 something. It's bigger than 1.4. So, but it's smaller than 1.5. So I already know that if I add up enough of its series, it'll be past 1.4, but there's no point on the series where it gets to 1.5. And what exactly is the thing it's going to? Well, that's what you would calculate if you're a computer calculating more digits of it. It doesn't have a periodic pattern, so you'll never hit an end with your computer having a job to do. However, you do have a pattern in the continued fraction. We can write square root of 2 like this. 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus forever. And it goes on forever, but it's periodic. 2, 2, 2, 2, 2, and all the denominators, 1, 1, 1, 1, 1, and all the numerators, and that extra 1 hanging out in the front. That is my favorite way of writing the square root of 2. Not talked about nearly enough. If you think that's cool, look at the episode on the main combo class channel later about continued fractions. The episode's called something with fractions and infinite or infinity in the title, like infinite fractions or something. That episode I made, it goes into a bunch of other examples, and I think these are super underrated. Way cooler than worrying about getting more decimal digits in base 10 about this thing is looking at stuff we can do with that. So square root of 2, it's just never going to pass that point. And we get the clue in this continued fraction or in the decimal approximation that we know which point approximately it doesn't pass. Which point exactly it doesn't pass is an irrational number. We couldn't write it down. We can describe it as this, or as the positive number where x squared equals 2, the positive solution to that. And in fact, many people forget this or don't know it, but this symbol does mean the positive solution, the primary solution. This does not mean, oh, we're also talking about the negative version. This, if I didn't say positive solution, has two solutions, plus or minus the irrational number approximately 1.4. This refers to one of them. A lot of people get so stuck up about, oh, you wrote this symbol and you didn't include one of the solutions. And they're not even right. This symbol literally in math means to only include the primary of the solutions, which in this case is the positive one. And so if you want to include both, you put this little thing right there. This with the plus or minus is the full answer to that. Or I could put it here. So, yeah, to those who want to know more about that, you can look at the video I put on here about that. And stay tuned, because that video is somewhat of a prequel to a longer one I'll do about some of my favorite infinite series. It will include how stuff like point infinite nines is an infinite series that does converge to 1, and that we are treating these things as what they converge on. So point infinite nines equals 1, which is, by the way that you understand the other rules of arithmetic, a factually true statement. Of course, any fact could be like, well, we don't have to play by that rule. We're the ones making up these symbols. But trust me, if you want your point infinite nines to not equal 1, you're going to have to relearn tons of stuff you thought you knew in different ways. That's almost the glue that holds together our base, is allowing every number to, have up to 2 representations in our base. Now, someone's still trying to understand the 2 tetrated and pentated thing. So I'll go back on that for one moment, which is, and whoever wrote principal root, they're right. I was calling it maybe the primary root casually, but the principal root is the technical way we could describe that. And here, if you're curious about the tetration, I'll try and explain it real quick one more time, because that was another one of the times where I got a lot of confidently incorrect comments on my videos. You usually get those on the shorts of people really confidently saying something wrong. Sometimes comically saying that, sometimes they say it's wrong, or sometimes they say it's obvious by including something wrong. For example, when I said, oh, here's a proof that the harmonic series diverges to infinity, you got a lot of comments saying that is so obvious. Anytime you add up an infinite amount of things, it's gonna be infinite. But that's not true. This doesn't. That adds up an infinite amount of things, the digits of square root of 2 when written in a given base. And that doesn't get to infinity. Half plus a fourth plus an eighth plus 16th doesn't pass 1. And so not all of them get to infinity. And so you got to be careful when you think something's obvious, because you might be underlooking it. In fact, this shouldn't feel obvious. It is you'd have to calculate an absurd amount of digits, not possible to do by hand or in your brain, for you to watch this past the number 10 or past the number 100. You could conduct proofs that are pretty simple to prove it, but as far as a gut feeling, you shouldn't necessarily have the gut feeling that that goes to infinity. If you automatically assume it does, you're actually getting something wrong, because there's many series that are barely different than this that don't go to infinity. So normally you get them on the shorts, the confident misconceptions, but the video on the main channel that blew up the most was the tetration one. So I got a lot of sorts of comments on that. That was the most popular so far of my full episodes. And we really need those full episodes to hit the algorithm more and again. So make sure that you watch and comment on the main combo class channel. This channel's doing all right for itself. This channel's going up really fast. So let's help that combo class channel catch up. And on that video, the main confident misconception I got was, no, 2 to hyperoperations 2 is not just 4. But it is. And it's because the hyperoperations, they're telling you how many to do this, how many of a thing on a certain level, and it includes the one at the bottom. So similarly, exponents, if I say 2 to the 3rd power, that means 2 times 2 times 2. I get 3 multiplied in total. If I say 2 to the 2nd power, I get 2 of them total. 2 total of the numbers I wanted in the lower level. So what about 2 tetrated 2, which can be written like that with the reverse exponent or with a double up arrow, among other ways. And for 2 tetra, you could also write it 2 with this 4th level of 2. And so these mean the level below a stack of these that many. So the level below is exponents. I have a stack of 2's, and the amount is 2. That's that. 2 to the power of 2 is an exponent stack of 2's that there are 2 of them. Similarly, 2 pentated to 2 would mean I have a tetration stack that has 2's in it, and there are 2 total of them. And that was this. So that also equals it. So no matter what level you're on, it equals the lower level looking the same until you get down to 2 times 2, which we know is 4. So if I were to replace either of these with a 3, it would fly upward because I would have a bigger stack in some level. But 2 does not grow under that game, under the game of I have a number, any hyper operation I want, and the same number. During that game, 2 being the number cannot grow beyond 4. And shout out to the name vinculum someone mentioned here. Not everyone knows, but the vinculum is named for some types of line used in math. So somebody is wondering how to find square roots. I'm not right now. I don't have like ready to go the really cool ways you can calculate square roots using very interesting equations and graphs. I will plan an episode around that sometime, but at risk of misexplaining anything, I'm not going to go too deep into how to calculate a square root right now. But I will just show an example of how I would go about it if I like had to give a rough-ish guess to what it is. Let's say I want to know the square root of 1,000. So, and it's not as easy as it looks. It's not like a multiple of 10 because the square root of 100 is just 10. The square root of 10,000 is just 100. But this is the wrong amount of zeros to simplify that way. So we for sure know it's more than 10 and less than 100, the answer there. But we could get a lot more detailed. I could think, I want a number x that times itself is about 1,000. So let's lowball and highball it maybe to get myself a range. I know that 300 is a kind of good lowball because that squared is 900. That's not that far off from that. So I could, in fact, from here, on this number, I'd probably lowball and add a bit to get there. I would think, well, I'm going to need a little more than 300 squared to get there. And maybe I would test out something between 300 and 350. Because 350, I can kind of gauge in my head, is going to overshoot it. In fact, we can think that 1,000 over 3 is going to look pretty similar to the answer, but it's not going to work because this times, well, no, wait, I'm thinking 30 squared. So yeah, what was I thinking? 30 squared. Whoa, okay, 30 squared is 900. That's what I meant. Between 30 and 35. Yeah, thank you for correcting. Unfortunately, we have a little delay for me to have decent quality until I can get a better internet, like if I have an Ethernet plugged in later. On the Wi-Fi, to make the quality decent enough, I have to have it have like a little delay between what you see and what's happening. I think it's about 30 seconds. And so, unfortunately, I don't see comments until 30 seconds later. But thank you for trying to correct me. 30 squared is 900. So to overshoot it, I was saying 35 would possibly be a little too much. If I took 100 over 3 and saw what would about 33 point infinite threes, well, this I can note, if I multiplied this by 33, we would be getting pretty close. But if I multiplied it by itself also, it would be too tall. We could test out something in the range of a little under that. And 32 squared, if I needed to, I could multiply this by hand. 2 times 2 is 4. 2 times 3 is 6. Get a 0. 3 times 2 is 6. 3 times 3 is 9. And add those. And I could see that we get 4, 2, 1, 0. 1,024. So 32 is a little too much. If I ran 31, it would be a little more than that. So 31 point something I would know is it by testing a few around. This isn't a super efficient method. There are other tricks you could use, but the easiest way would be to undershoot it and or overshoot it to get a little range of what it's near. Now, as for math book suggestions, I have suggested some math books in the past. I will suggest more when I'm in my room sometime. I'll suggest them when I have them to show you. As you know, if you want one suggestion that's somewhat similar to a lot of the stuff I discuss in some number theory concepts, I highly recommend The Book of Numbers by John Conway and Richard Guy. There are many other books I recommend, so I'll show you more when we're in my room sometime. Another that I recommend, that if you'd like my videos that you'd probably like, is any of the articles written by Martin Gardner or any of his books that are usually collections of those articles. So, other writers shout out real quick: Raymond Smulyan, Clifford Pickover. Those are also some of my favorites that remind me a little bit. Also, shout out to Matt Parker, who not only makes the channel Stand Up Maths here, but he has written 2 great books as well. Speaking of 31, it is true, funny enough, someone was saying a rough approximation for pi is someone saying that square root of 10 is a rough approximation of pi, but a better one is cube root of 31, which is kind of funny because here we were saying 31 is a relatively close integer to its square being 1,000. So that tells us that somewhat close to the 6th power of 1,000, I guess, must be pi. Let me look that up. I mean, the 6th root. Yeah, so since the 6th root, wait, let's see the square. Yeah, so the best approximation for pi within that range is cube root of 31. I actually made a short where I said, I found some others, like there's a 5th root that's a good approximation. I was like, what roots are closest to approximations to pi? And some people left really good comments on that short with more details. But it's really good. It goes 3.14138. It got some good digits. So someone said, what was the book I recommended about logic puzzles? One of the ones that got me hooked as a kid that I still highly recommend is called What is the Name of This Book by Raymond Smulyan. So I don't have my computer easy to go to the computer screen right now. I'm staying on like this camera for today. So just like the webcam thing. So I'll show you when we're in my room some more of his books. I have that one and some others in my room. So, lots of cool comments and thoughts. We will give one more shout out for today's theme to Mod 3, which will return in many future contexts, because whenever we come across a type of number, we already often think, is this even, is this odd, or is this sometimes could be either? But we less often think, is this type of number always or never some of these? Like how square numbers were never pre-3 even. So we'll find other times where certain types of their mod 3 status comes in handy. And like I mentioned, when we get to composite mods, we can sometimes express them in terms of lower ones. And so, for example, next Modular Monday, when we'll talk about Mod 4 at a similar time next Monday, that will be a mod where we're looking at status of evenness and doubly evenness. Multiples of 2 and doubly even numbers, multiples of 4 and the ones between those. So it's going to have some similarities, although differences, to an expanded version of the Mod 2 table. But even closer linked is how Mod 6 can be fully built from your 2 and 3 pretty easily. So remember, if we ever are going to switch to another base as humanity after an apocalyptic-like event, although many recommend base 12, As I will clarify more when we talk about base 12 more, a lot of the cool patterns I've discussed about base 6 in the past are the cool things people like about base 12. And then there are or ones that base 12 doesn't even have that base 6 does have. Base 12 is a little clunkier. If you want, base 6 gets a little more, if anything, of the good traits of base 12 and base 10, as weird as that sounds, because base 10 is good at handling 5s and 5ths. And although base 6 doesn't have 5 as a factor, 5 is the number 1 under the base. 5 is the new 9 in that base, the biggest single digit number. And so 5 has a lot of easy divisibility traits in base 6 and does make it easier to digest multiples of 5 or 5ths or things in base 6 or mod 6 because that's a neighbor of the base number, even though it's not a factor of the base number. And so you actually get some of the good 5 divisibility stuff, a little hint of that in base 6, as well as all the good ability to process 3-evens that base 12 has. And for missing out on the ability to process doubly even stuff, you are a lot neater in most other ways. So base 12 is pretty bad at writing things like 1/5 and 1/7 compared to base 6. We'll go more into those in the future, but I will, of course, clarify. Base 12 is better than base 10. If we had a choice, and it wouldn't be too catastrophic to have to translate all the old stuff, it would be better for the future of math to count in either of those over base 10. Base 6, I recommend more, neater, cooler. Base 12, almost as good, far better than base 10. Both of them, really, the main best trait about them is their ability to process 3-evens and 3rds. 3-evens are more common than 5-evens in both math and nature. Someone's mentioning a logic puzzle called the 100 blue eyes problem. Yeah, there's a lot of good logic puzzles where you have to deduce things based on like eye colors or hats or things like that. Some of them, when you have a large number of people, can seem unsolvable. And whoever mentioned 1/7 in decimal form, yep, super weird. Looks kind of cool because it has these cyclic properties, but other numbers have those too. But it does have these cyclic properties that are neat, but it's not the only one who could do that if we switched bases or whatever. It's very weird, but it's not that weird in base 6. It is weird in base 12. Let me look them up real quick. I'm just going to describe them with my words, but I'm going to look them up real quick. So 1/7 in base 10 is 0.1425, wait, here, 0.142857, repeating. That's pretty clunky for a 1-digit denominator. You know, not very ideal. 1/7 in base 12 is actually still clunky. 0.186 they say next for whatever digit they use to call 10 as a digit. 3, 5, and then it repeats. It's still a 6-digit string that repeats. What about 1/7 in base 6? 0.050505. It's a 2-digit string that repeats. 3 times shorter and simpler than either base 10 or base 12. Thank you a lot to M. Johnson, too, for the Pi amount donation. Those always help. To all the random donators and Patreon supporters and stuff. Also, to anyone who has donated an amount that is, we will say, Pi or more, so let me know too, M. Johnson. Let me know in a comment. Ideally, a comment that's on this stream after it posts, or on one of my last few streams after they have posted as the video, because that's easier for me to make sure I find than in the stream chat, which actually takes a while to process and vanishes for me for a bit after it's processing the video. Let me know if you want your name to be included with my Patreon people in a whiteboard for, you know, the combo lords who pitched in, which is mostly the Patreon people. But if anyone who donated randomly, at least we'll call it pi amount of US dollars, then at least a little under pi, because $3.14 is a little under pi. So if I said at least pi, the nearest cent would have to be 3.15 to be at least pi, because pi is in between those. We'll say at least the fraction right under pi, at least $3, because that's actually the Patreon minimum too. So at least $3. Let me know if you want your name included on the whiteboard where I'm thanking people. If you are also such a super fan that you think I would recognize your name from you commenting a bunch on this channel or the other channel over time, shoot your shot too. Maybe I'll include some people who I recognize the names and they've commented a ton. But let me know if you want me to include you on a comment after the stream to people who that applies to, because the default is my Patreon people plus whoever lets me know. And that's basically for in the finale episode, one of the last scenes I have to film. We've already done the shaving. We've already done the final desk destruction. We've already done camping and cooking dinner and a field trip and other surprises. And so one of the last scenes to film for it is an extended version of credits, where instead of just sticking credits on an end whiteboard, I'm going to run through a few credits so I can have maybe some cameos from some people who really helped me, like people who filmed with me or friends, family, stuff like that. May have some little cameos to thank them. And I will have some sort of whiteboard thanking people who are a fan, who help with any money, because that really helps, is part of the reason why I was able to quit my day job in March and think that I have a good enough time. I mean, I'm going to be living at home for a little bit. I have to be very careful about spending money. I can't eat out often at all. But with that said, I have cheap taste, so that's totally fine. And I would rather have quit my job and have free time and be tight on money. I do think that I have the ability to eventually make this a sustainable career, because we've been growing at a good, fast rate here. I made a 100,000 subscriber special really recently, and we are maybe by now, let me see if we have yet or not, past 107K. We are on the hair of that. And everyone keeps popping into the stream and asking why my face is shaven. I'm going to have to explain this too many times. Watch the finale when it comes out. Really, I wasn't even going to show this. I almost did all my streams for the rest of the month voice only, so I would save this for the finale. But then I wanted to do my 100K subscriber special with my face, so I ended up just cat out of the bag. But it's really only the stream attending gang who will know about this. There are some viewers on that channel who have no idea that I look like this, who are just going to see me shave it near the beginning of the finale episode and have it for the finale. Someone's saying $22 over 7, which is very close as well. That would be a repeating but infinite amount of cents. So we would need fractional cents going on forever, although in a repeating fashion. So we'd still have to round that one up, but 22.7 is easiest to remember, along with cube root of 31. Cube root of 31's extra good, but easier to calculate would be 22/7 for just getting the start of it. Really, though, those don't get you better than knowing 3.14159 or whatever. So, if you want to get that many digits, you're going to need a slightly better approximation, which there are. In fact, that continued fraction right here I was showing before all this clunky stuff got in the way? Well, the continued fraction with only ones on the numerator, but different stuff on the denominator for the square root of 2. Finding right here the convergence, what this has added up to at different points, can give us good approximations of it. And you can use the pi continued fraction, cut it off at different points with a simple rule, and get your best approximations. So let's see if we have gotten there yet. We are so close. Oh, whoa! We literally are at 107,003 subscribers. We are 107,003 subscribers. That's great timing for me to check. Awesome. Thank you all. This has gone so fast this week. I love it. I'm here to trick all the people on the Shorts tab into liking numbers and learning. So, to anyone who is new, thank you. I hope you stick around as a combo lord. And remember that my best content is the full episodes I make for the combo class channel. This is my channel with more stuff that I'm less perfectionist about. But if you want my best stuff, make sure to check out the combo class channel. Right now, what it has is the final exam as the latest episode, which, like I said, sometime between now and my Thursday stream, I will have put out the answers in a bonus video here. I was intending on dropping them around today, but with all the finale filming and stuff I'm doing, it might end up being in 1 to 2 days from now. But within 1 to 2 days, I'll be dropping my version of the answers to the test. Skip it if you might do the test in the future. No reason to watch. Even though, like I've said, I'm shooting my viewing in the foot by telling people not to watch a video. It's better for your brains. I'm going to tell you once, don't watch that video. Just for that video. Watch all my other videos. But don't watch that video if you might do the final exam at some point in the future, because it's good for your brain. So, what else do we have coming here? Well, I kind of want to play around and show you folks some graphs. I think what I might do is I need to run inside to go pee, and if I continue the stream, I'm going to grab a cup of coffee as well. And then maybe I'm going to switch us to looking at graphs. That will take a moment to set up, but it's going to be fun. I know viewers like when we do graph stuff, and let's see if I somehow have that set up already or if this is going to vanish me. It's not set up yet. So let me get my computer in the background, and then I'm going to run inside for a brief moment. But while I run inside, it'll look cooler if I have a cool graph started. Now, I have found new types of graphs. So we're looking at, by new, I mean probably someone has looked at them before, but who knows? I've looked at so many combos of shapes on Desmos that eventually we're going to have looked at so many that it's improbable that someone's looked at all of them. There's so many, the amount of combos you could put between little things grows at a factorial-like rate. And so some of the new ones that I'm looking around today are ones that I haven't really tried yet, and it was just a thought that popped into my head as a new way we could combine shapes, which is that we've done exponents, we've done sine-related things, but what I was trying here was putting stuff like sine and tangent in the exponent. Like, instead of saying like sine of x squared, saying like x to the power of sine x and stuff like that. And I got some cool new shapes, including one that is going to sound so random and randomly specific, but one of them looks like a burger factory or a burger restaurant or something. You're going to be like, what are you talking about? There's way too specific for one equation to look like a burger restaurant. I swear, there's a burger in it. It's this landscape, and there's multiple burger-looking things in it. So, where am I? I'm in my combo classroom in my backyard, along with the birds, and it is nice and calm. It's been raining out here, super muddy, but we're in between rains. The birds are loving the little bit of sunshine. We may get some visits from the cats out here. Now, someone's saying they're still confused about 2 pentated 2 and 2 tetrated 2. Do you mind linking what? I'm not surprised ChatGPT is wrong. Never trust ChatGPT for math stuff. Look at my streams where I ask them stuff. They are literally wrong more than if you threw a dart at a wall randomly where half the stuff was right answers. They're literally more wrong than if you asked a 10-year-old to guess the answers. So with math, it's comically bad. But I'm curious what websites you had that said 2 tetrated 2 or 2 pentated 2 is larger than 4. So let me know what website that is, because if you pentate 2 to 2, it is definitely 4. So let me know what website you saw that doesn't say. Here's an example. Look at Wikipedia's article on pentation. Wikipedia is definitely among the correct ones, where they say what it is, which is 4. You can see it on that page as 2 to the 5th level of 2 equals 2 to the 4th level of 2 equals 2 squared equals 4. So if you don't want to trust Wikipedia, look at more sites, because they're also going to say that. I'm not sure what site you saw. And if you count the I'm not sure why it's, I mean, I get that it seems like it could be confusing because we're going to a higher hyper operation, but most people would agree that 2 to the power of 2 isn't bigger than 2 times 2. And these are a direct extension to that. Multiplication to exponentiation is exponentiation to tetration. So if 2 times 2 isn't any different than 2 to the power of 2, it almost should be a gut feeling that 2 tetrated 2 should be the same. It's an exact extension, and it's been the same already when we extend it. That's not true if 3's are in the mix. 2 to the power of 3 is not the same as 2 times 3. So we know that one's going to change as we go up the chain. But 2 times 2 is the same as 2 to the power of 2. So for some reason, people don't like that it also equals 2 tetrated 2 and stuff, but it does. The stack includes the one at the base. So I recommend, like, look more on the Wikipedia one. Just from me pulling it up right here, it looks like a decent article about it. So, let's see. I wanted to switch us so we could look at some cool graphs. Now, that's going to take me 1 second, and let's see. I need to... I'm not a tech whiz. I'm so bad at making this work functionally. So I will shortly have our graphs up, though, including one that's already built here. So let me get these ready. Okay, so how am I going to do this? How does this look? We can stretch this a little bigger. I need 2 monitors or something so we don't get infinite portals when I do this. All right. There's our graphs, and... oh, no. I need me. There's our graphs. And here is me. So, what's going on in this wacky graph? Well, there's a lot of stuff I got on the side here, and I put a few of them on a row for fun, and it adds them in different colors, which is fun. But let's remove this wacky thing for a moment. That was the one with all the sliders, and although this is a little glitchy, we can see they're supposed to be meeting at those points. It's just glitching it a bit. It's hard for it to handle when you put sine and an exponent. But this is sort of neat. Look at this. The red one is y is less than or equal to x to the power of sine x. And then we have that with the y and x flipped. Not all the y's and x's, not the one in the sine, but the front one's flipped. It's this thing up here. As the blue one. Now that's pretty neat. What if I tried putting the power on both ends, like y to the sine x is less than or equal to x to the sine y? I get this wacky web. That's pretty neat. It becomes more and more square-like as we go up there. So if you met this grid all the way out here, you might think it was a square grid, but then we get bendy. And also like these little creatures hanging on the wall, like little bits of slime or something. So that's that fella. What if I say y to the sine of x is less than or equal to the sine of all of that on the right? Well, we get my burger factory. Tell me that this is not a burger. These are burgers with different amounts of fillings, are they not? Tell me that's not a burger with 4 types of ingredient. This one over here, for example, has 8 types of ingredient. This one Desmos is having trouble looking at, but there we go, it's got it. It has 6 types of ingredient. So these are literally burgers. Don't they look like it? Now we can make them even more burger shaped, kinda, if we fiddle around with adding some coefficients to change. We also get an hourglass there. So we get our hourglass keeping track of all of our burgers. And the reason I called it a burger factory sort of is it sort of looks like these are weird machines that are like containing ingredients getting pushed down, and they're pushing out burgers at the bottom. This machine can make 2 burgers in a stack. There you got your machine up there, and then your burgers. Here we got another machine, some more burgers. For those who don't eat meat, you can pretend it's an Impossible Burger. Those are really good too. So, or a sandwich on some type of loaf of bread that you cut in half. So, I would like to hear someone try and tell me that's not a burger. Tell me what else you see in this graph. There's other cool stuff here that we could interpret this as. I love when our graphs show us things that look mildly similar to something that you could see in the real world. And this is the first time I saw a burger. So, I'm going to now pull up the chat on my phone so that we don't have it delayed in the background. And like I said, although we're shifting to graphs, I am going to run inside to go pee and get, hopefully if there is still some in the pot, some cold coffee. And in the meantime, what I would like to hear is, what else do you see in this graph? What variations do you think should be added or tested? And what sort of cool wildlife do you hear or see in the background? I will be back in about 3 minutes. Okay, I'm back. All three cats were on my porch. Unfortunately, I don't know if any are going to follow me back here. But maybe we'll get some cat footage later. The porch is the hardest place to film, although I film there sometimes you got to point a certain way because I don't want to show my address. Although I do have my private mailbox address. As a reminder for any fans, if you have any broken clocks, I am now accepting broken clocks or dice or calculators or other cool items you think you'd want to see in the background of grade -2. And hopefully throughout grade -2, we will have some clocks from some of the viewers hanging in the background. Of course, don't send it if you'll feel too bad if you see it get destroyed, which it might. But I'll try not to destroy anything until it's done enough great teaching. So, also, the accelerated lifespan gives things a more fun, unique lifespan. Not in terms of a human, I mean, don't accelerate your lifespan too much. In terms of a clock or something. So, thank you all for joining me. I should put, oh, damn it. No, it's right here. Okay. I do have the chat. So, taking a peek at our chat, we do have people wondering about the Burger Factory, and they would like to see more parts of the Burger Factory. One comment also notes if you take 3 squared, you get 9, and if you divide by 3, you get... And we can note on our Mod 3 episode that I like to call multi-threeven numbers that are multiples of 9, because they're threeven to at least the second level. We could also define doubly threeven numbers as with that nickname, and you have to be careful with your definition to clarify whether doubly is going to mean only doubly and not triply, or to mean at least doubly, which typically it just means at least doubly, like doubly even. And someone notes that 3 squared is 9, a pure threeven, I call them in fact, the ones with only 3's in their prime factorizations. Basically the powers of 3 apart from 1. But if you divide by 3, you get 3 to the first power. Divide by 3 again, you get 3 to the 0th power, which is 1. But if you try that with 0, you have to divide by 0, which is impossible. So, and what you're getting to there is why 0 to the 0th power has some glitches and is often known as an indeterminate, except in certain fields that assign it a value of 0 or 1, while knowing that they're assigning it that. It doesn't really logically fit either without contradictions you have to make sure to work around. So, although some fields assign 0 to the 0th power a value, slightly more often 1, sometimes 0, but those are not on the big context, its value. On the biggest scale, where we're looking at all fields of math, it is indeterminate. And there is a huge worm here. Oh my god. You folks want to see like the biggest earthworm of all, not of all time, but like maybe the biggest one I've ever seen in my yard. Oh my god. Look at this massive worm. Do you see that worm? That is a huge earthworm. Whoa. So, I just had to show that for a minute. Shout out to the worms. They help decompose and stuff. A lot of people are anti-worm because, you know, certain types of worms are parasites and stuff. But earthworms, we are fans of. We are very pro-earthworm in combo class. So, Burger Factory, higher levels, it gets a little glitchy as I move up here, but we do have this thing. Look, the hourglasses, this one wasn't quite formed. It was like wanted to be an hourglass, but couldn't quite. Then if you go diagonally upward, you get hourglasses. Above them, you get these sort of hourglassy things. Sometimes you get other stuff, and you get these little pointy things under start to develop. And as I go over, these burgers have more and more fillings. So the burgers on this side of the factory are hard for the computer to get. If I really zoom in, I can see this burger's filling. So that's this burger's filling. But the graph has a hard time showing me all these. It might be that I'm using the online version. You know, sometime I'll try and download some desktop versions of graphing software, which might make it less glitchy for us. For now, I'm using Desmos, great free, cheap, I mean, not cheap, it's free. Great free site if you ever want to do, by cheap, I mean like simple. It's not going to be able to do insanely complicated stuff, but it's super good for a simple graphing calculator. So these burgers have so much filling, it gets hard to see them. What's your ideal burger? Which one would you go with? There's only so many toppings you need in a burger before it gets hard to eat. That's a whole nother story. What's up with these restaurants nowadays being like, try the Golden Infinity Burger. It's this tall and it has a whole lobster in it. It's like, how are you supposed to eat that? You cannot eat it as a burger. So, come on. If you own a restaurant and you make a burger and it can't fit in someone's mouth, take off the buns and don't call it a burger. So I'm going with these burgers have too many fillings. My ideal burger would be somewhere around this fella or even this fella. You know, maybe 6 fillings. That's a good amount of stuff in the burger. Let's see what the burger has. You got your burger. You got maybe some cheese and some bacon. Sorry we can pretend they're vegetarian versions to anyone who's vegetarian. I was vegetarian actually for several years, for 5 or 6 years in the past. I currently eat meat, but sometimes I eat the Impossible burgers just because they taste really good. Then you got like some lettuce, tomato, and onion, and yeah, that's pretty much the right burger right there. This one, if you want to have a couple extra special toppings. This one, if you want to keep it simple. But what about mutating the burgers? Can we move them at all? So, and someone's wondering where pie's hiding. That's a good question. The fact that I put signs in these things does make it likely that we could find pie lurking somewhere. And what about right here? Da 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 da. There's a pie. Da 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 da. This gets really thin, but I'm pretty sure this green line gets past the 3.14. It's just so thin at that point. If this approaches that and it's not pie, I would be pretty shocked. So that looks pretty pie-like. Now, and maybe what about this point right there? The maximum out right there. That looks pretty close too. I bet you there's a ton of pies hiding on this thing, and powers of pi and multiples of pi. So vote for your favorite burger. We're going to start mutating them. How are we going to mutate them? Well, the simplest start, and I actually did note that when you try tangents in these, normally it makes it way crazier. It kind of didn't. Tangents, well, no, okay, it made it way crazier, but less burger-like. When you zoom out, it was harder to see anything. So these are good little, like, connected, weird, like, infinity blob burgers or whatever. Let's put a tan there. These tangents did not make burgers either. These made... Oh, whoa. From this scale, they do look like if you had the bottom half of a burger. Is this like the burger construction factory? Or this is like an open-face sandwich? So it gets infinitely dense on there. So that infinitely dense bit, that looks like sprouts or something on an open-faced sandwich. So that's if we put a tan there. It's really giving the graph trouble. I hope it's not making the stream super glitchy because my computer can only do so much. That's if we put it there. Now we're going to put them back to signs. Here's the thing though. The equation right under this, I'm going to get rid of some of the other ones. The equation right under this thing, under my burger factory, is the burger factory if I set these all to 1. I put a bunch of multiplying constants, A, B, C, D, multiplying by stuff, And then I can tweak them to set them to different levels. So what we're going to do there, you might not be able to see all the dials, but I have dials for A, B, C, and D I can control. So I'll put whatever dial I'm controlling high enough for you to see at the given time. When they're all set to 1, this is the burger factory. Same thing. But if I change them, I now have different ways of mutating the burgers. So let's keep our eye on my 3 favorite burgers, the 4 slicer, the 6 slicer, and the 8 slicer. And there's actually a few of some of these. You got another 6 slicer there and another 8 slicer there because these machines made a couple. Only one customer ordered it light. A few of them ordered it like that. So let's tweak A first. This is sort of shrinking the burgers a little down that way a bit. You want them to be thinner burgers for some reason? We can go that way. Now, what if you want them to be wider burgers? Then we could start going this way, but you can't go too far. If the burgers hit each other, it's all over. So you can widen the burgers a little bit. Now I got a little pointier and wider of burgers. But if I go a little further, this weird thing at the bottom, you see this like thing that started to be created down here, is going to take over. So I go any further down, and it has taken over. And now we just have Swiss cheese. The room has become Swiss cheese. Going back to 1, we can see, what if I had adjusted a variable in there, where the X is instead? That's going to sort of slide these fellas over, as well as mushing them a bit, and simplifying their ingredients. So as they slide, their ingredients simplify. Now we got like this tall sandwich where we have like lettuce, tomato, and then some big hunk of meat or fish or something, and then 2 more ingredients. This is someone ordered that without the filling. This is a light version of that. So if we're sliding B, we can sort of minimalize the toppings and give them different shapes. Sort of make one bigger topping in the middle, if that's what you're going for. But they get a little too pointy as you go too far. If you take them the other way as well, we can see that we are stretching in similar ways. We're getting wide burgers with interesting stuff. These are interesting. These could be a cool type of sandwich. I like this fella. Look at this sandwich. Looks a little imbalanced, but pretty cool. Same with this sandwich. So now we're getting some good sandwiches. Now, we'll put B back to 1, and now we're going to try messing with some other stuff over there. So C now is going to get its time to shine. Ooh, C is giving them some more extra glitchy feelings. So, there we're getting similar weird glitchiness of different sorts as I generate different types of burgers. Ooh, well, there is just the uncut loaf of bread. So it's like some bread, splitting the bread. I split the bread into loaves, separate the loaves a bit, and then start putting in your fillings. Oh, whoa, look, as I go over here, it's like the burger in process. Oh, that's so cool. Is there a way to, like, pan over here? Does anyone know? Is there a way to, like, tell Desmos to, like, slowly pan that direction? Look, it's like, from an egg, I shall hatch a burger. Now, this is just going to take a little while, but watch the bottom row. I got my buns, putting some meat in, splitting it, got some cheese, some tomatoes, some lettuce. It's the burger creation. Now you can't take it too far. Oh my God, this is like the perfect burger. Look at that. We got an actual burger looking thing in the middle, bun looking things, and toppings between them. Isn't that wild? And welcome to the people saying hi. So thank you to the new viewers. Today we are just doing some fun modular chat as well as graphing shapes, but there will be a lot more fun videos of various sorts. someone is mentioning various suggestions for cool stuff on the stream. I'll definitely take those into consideration. Someone's wondering how are ellipses and parabolas related to a cone. You could slice a cone with a straight line to get them. Well, parabolas are very much so. There, where if you take a cone and you slice there, you can get good shapes, your conic sections. Now, let's look at one more modification we could do. Although that made a really good burger right there. You got to agree that some of these burgers are at like, for a burger, that's pretty maximal. That's what you want your graph burger to look like. If you wanted a bunch of toppings, you could take it one level further, and we're going to get a similar one right here. There's another perfect burger if you wanted a few more toppings. Or maybe this one. That one's even more perfect. Wow. So, now, last one to try is D, and we can do multiple at a time if we want. Uh-oh, I'm all the way over here. I'm in the place where they put too many ingredients on the burgers. Oh my god, I'm on Pi 100. So, gotta get back home. Run, I'm running through the burger factory. So, we shall call this here forth the burger graph. And the burger graph might not need all of these adjusters in here. Theoretically, this is the simple burger graph, is just this one. But with some of these adjusters, you can make those ideal burgers. Now, one last one we could try was D. D shrinks the burgers. You want sliders? If we use D and C to get... Wait, no, D and... was it B? Yeah, look. Do you want, like, sliders? You know, those mini burgers? We're shrinking our burgers now. There you go. I got shrunken burgers. I can make my burgers at any size with the right combo of glitching stuff. And if we want to make it go really crazy, we can go back to seeing what happens in this whole landscape. Here's a cool sector of the landscape when things are like this, like half merged. Whoa, that's cool looking. It looks like a maze. Whoa. Now what happens when I adjust some more of these? Creating different strange mazes. Whoa. That's trippy. Whoa. This looks like something you'd stumble across in a field that aliens created. I mean, no. Aliens probably didn't actually create the crop circles people talk about, but I mean, one that you would be like, wow, that looked alien-like. And then you go up here and there's another. Also looks like amoebas. So, this is when we went into the whole landscape. Lots of adjustments you could do here. So there's so many different states you could get this thing to go in. That's a weird new dish the restaurant might serve. Whoa, this is the crazy burger right here. Be careful when you eat this burger. Whoa, that's a wild burger. It's more of a sandwich. It's actually a pretty good looking sandwich if these middle ones are like slices of some particular thing you wanted to eat. Even looks like realistic with gravity. They're like curving a little bit. So, yeah, what else is going on here? These are the crazy burgers. Technically, if we zoom in, we can see what's going on some of them. I don't think they have infinite depth. I think they just have a lot of stuff. Wow. This is like a croissant. That's what that one is. You zoom in far enough, you're like, okay, there was distinct little layers. But if you just look at it or bite it, it might look like that. So, this landscape's pretty wild. And at the bottom, these are the burgers that didn't make it. Okay. Well, that's most of what we're going to be looking at our burger graphs for today. Whoa, what was that? Never mind. Something weird happened in the middle. Whoa, it hits that just for a second of a cool look where it's like partially there. No, they're all connected. This is like the back of the burger factory where they process all of the parts. All right. So, a lot of fun things we can look for in equations, and today's was some equations make little burgers or sandwiches. And I'm particularly fond of this type of equation where things have their own little islands that you can mess with as if they're little creatures or foods or whatever. Those are always fun. So, we are going to wrap up our stream before long because we've been going for a while. And in this week, like I mentioned, we'll have our quiz answers. We'll have another stream on Thursday, if not sooner, and we'll probably have some bonus videos. I mentioned one might be coming out about highly composite numbers, and so I might do that one and or some other bonus videos on this channel this week, as I'm mostly spending my energy this week on working on the finale episode, which just has a bunch of crazy scenes about the building of the grade, a bunch of stuff you haven't seen, and some crazy transitions. Now, the finale's cool, and just as cool will be the intro to grade -2, which I was originally thinking might be ready at the very beginning of April, but the finale, I'm trying to get it just right and not rush it out. So if the finale comes out late enough in March, the intro may come out like a week or so into April, but that intro is just a short little episode where you see all the new types of tricks we might have up our sleeve for grade -2. Some rare stuff that I can't tell you about yet. And then we'll jump back into math topics on the main channel too. So, thank you all for joining me here. I can't really go back and answer every single question, but thank you for leaving them. Remember to check out all the cool links like the Discord and stuff and the subreddit. Or if you're supremely helpful, the Patreon, which does have bonus content too. And like I said, let me know if you are not a Patreon person but contributed in some way you'd like to be thanked in the finale, because I will be thanking people. Let me know in a comment when the video posts. And to anybody out there, thank you so much for joining me, even in this chaotic phase where our classroom is very empty-ish. Let's go to the full classroom for a minute. The classroom is very empty-ish, and I have half a beard and half of my classroom filled. So, more space here than usual. So thank you for joining me for the halfway point between grades. I mean, not the halfway point, but the halfway point of the transition. So, for those who don't like the beard like this, don't worry. I'm embarrassed going out in public like this. I want to shave it soon, but I'm going to shave it after I do all the rest of the finale filming. If you have something weird, like I figured when I was young, I thought this a while ago, like if you have a long beard and you're going to cut it, why not cut half of it at least just for like an hour or two, just for fun, just because you have the chance. And then this time it turned out to be more than an hour. Well, in any case, love you all. Thank you for joining me here. I'm going to log off and catch you again another time soon in some sort of bonus video or another fun stream. And I hope you all have a great day or night, whatever time